Hi everyone, thanks for coming to my talk today. And today I'm going to be talking to you about Drizzle, which is a low latency execution engine for Apache Spark. This is joint work with Aurojit Panda and Kay Osterhout from the AMP Lab, or now known as the RICE Lab at UC Berkeley. So before I get started into Drizzle, a little bit more about who I am. As Doug mentioned, I'm a PhD candidate at UC Berkeley, and most of my dissertation work has been focused on how we design and build systems for large-scale machine learning. I've been an Apache Spark PMC member from the beginning, and I have made many contributions to Spark Core, MLlib, SparkR, as some of the components in Spark. But the focus of today's talk is specifically going to be low latency stream processing, and in the context of Spark, especially Spark streaming. Now, the latency of Spark streaming is a topic that comes up in a number of contexts in user mailing lists, which, for example, ask questions like, how do I set the right dstream batch interval, and how do I configure Spark streaming to get low latency? In a number of other discussions in terms of what features of Spark streaming users are happy with or not happy with. For example, there was this recent mailing list thread about how achieving low latency, high throughput, and stability are like important characteristics, and that it's difficult to do that with Spark streaming today. And even in the user guide, for example, where we have a number of different documentation in terms of how we can configure Spark streaming in order to improve the latency. Now, given that there's so much concern over low latency, one of the objectives of this research project that we did at Berkeley was to study where the latency goes when we are doing some of these like large-scale stream processing jobs, and see what are some of the techniques we can develop in order to lower the latency of these jobs. So to get to that, let's take a step back first and look at what are some of the goals that we have when we're doing large-scale stream processing. So the first goal, which a number of users think about immediately, is in terms of performance. Specifically, if you have a streaming job that's running across a large period of time, you would like to achieve very low latency and very high throughput across a number of machines. And this is especially harder as your cluster size, let's say, grows and scales to handle a large amount of data. But in addition to performance, users also care about other aspects of stream processing systems. So one of the most important things when you're running on such a large cluster is in terms of your system being more adaptable. So what do I mean by adaptability? So for example, fault tolerance, where machines could fail, or some of the slow machines could slow down your job, are examples where you want the system to be adaptable and handle such events seamlessly. But it's not just in terms of fault tolerance. Adaptability also applies to scenarios where you want to improve the performance of the system. So for example, elasticity, where let's say we add a bunch of machines to the cluster, is an example where we'd like our system to adapt to the changes in the cluster and improve performance. And finally, earlier on in the keynotes today, Michael talked a little bit about query optimization, and specifically how in Spark we have this like SQL engine that works and improves performance. And this is also a case of adaptability, where over time you want your query processing engine to adapt to the kind of queries and data that you see. So given that these are our goals, how do we go about achieving them? And to do this, in literature, if you look at the history of like stream processing systems, there are two main sort of execution models that have been used by systems developed so far. So one of the most classic execution models is this model that I like to call as the record at a time execution model. And in this case, what happens is that at the beginning of time, we have a centralized driver or a scheduler that goes ahead and launches a number of these operators that are going to run on various machines. Now, these operators start, and they read data from the input sources, and they also exchange messages with each other in order to make progress over the course of time. Now, the characteristics of this model are that we have these long-lived operators that live on every machine in the cluster. And then we have some mutable state at each of these operators, which is making sure that it's updating whatever is the intermediate data that is getting processed. And to do fault tolerance, typically in this system design, we take distributed checkpoints using something like, let's say, the Chandy-Lamport algorithm in order to give you fault tolerance. Now, this is a system design which is used in a number of open source and other research projects, from classic designs like in streaming databases like Borealis and Flux, to more recent research projects like, let's say, Naiad, or open source projects like Apache Flink. Now, in contrast to this model, there's the second model, which is the batch processing model, that probably users who are more familiar with Spark know of this better. So in this model, what happens is that we have similarly a scheduler or driver that launches some tasks on these machines. But in contrast to the previous case, these tasks actually coordinate with the centralized driver as soon as they finish execution of whatever quantum of work that they're given. Now, in order to exchange data between different stages, there's a shuffle operation that is coordinated again by the centralized driver. And this allows the centralized driver to make some clever placement choices on where these tasks are placed. And similarly to the previous stage, there's some coordination that happens at the end of one of these shuffle operations. So what I've shown here is, for example, one micro batch of execution, as we call it in Spark streaming, and future micro batches proceed similarly. Now, the key characteristics of this model are that we have centralized task scheduling, which is shown in these red boxes out here. And because we have the centralized task scheduling, we can actually do more intelligent things for fault tolerance, which are like lineage and parallel recovery and so on. And finally, the scheduler or the driver can also provide other forms of adaptability, like to adjust to new machines being added to the cluster or to do straggler mitigation and so on. Now, this model, as I said before, is definitely used in Spark, but it's also used in a number of other systems, like systems based on Hadoop or Google Flume Java and Microsoft Dryad and so on. So just to put them back together on two planes, on one hand, we have the batch processing model, which lets us use lineage for partial results and have these micro batch boundaries where we do some optimization, but suffers from more high latency when compared to the record at time systems. On the other hand, the record at time systems provide much lower latency, but have more complex mechanisms and find it difficult to do things like elasticity and straggler mitigation out of the box. So the main question that we asked in this research project was, can we actually achieve the low latency that these record at time systems are achieving with a design like Apache Spark? Or to put it another way, can we actually unify the benefits of both of these models and sort of get the best of both worlds? And the key reason we think this is possible is from this single design insight that we have. And the main design insight here is that we can actually do execution at a different granularity than at which we're doing scheduling. Or to put it another way, we'll do data processing at a very fine granularity in order to achieve low latency, but we'll do coordination at a more coarser granularity in order to reduce its overhead while still retaining some of the benefits that we had before. So this is the main idea behind Drizzle, and there are two main techniques in Drizzle, group scheduling and pre-scheduling, and I'll walk over at a high level how these techniques work today, and then I'll give you some of the evaluation on how these techniques actually help in practice. So let's start with group scheduling. And before we look at group scheduling, let's do a little bit of a recap on how Spark streaming works today. So we have this scheduler that I've mentioned before in the talk right now. And the way it looks is that there are a number of these micro batches that are created by the streaming engine, and then they're submitted to the scheduler. Now, the job of the scheduler is to place these micro batches on a cluster that you are running on. And as soon as the first one finishes, it places the second one and the third one, and so on. Now, in order to understand how the scheduling works, let's zoom in a little bit more into the heart of the scheduling system that is present in Spark. So at a very high level, what the scheduler is doing is that it's trying to find out where each task that you're submitting should be placed. And to do this, there are two main data structures. There's a list of tasks that need to get scheduled, and then there is a list of machines on how many cores that are free on each machine. Now, the scheduler runs a number of algorithms given these two data structures. These algorithms try to, for example, associate locality so that you read data from where your inputs are, or to share your cluster appropriately across a number of users. And the output of these algorithms is a mapping. It's a mapping from the host name to a list of tasks that will run on that host name. Once we have this mapping, we can then serialize and launch these tasks to run on the appropriate machines out there. So how expensive is it to do this kind of scheduling, especially when we have very low latency tasks that we are running? So to measure this, we ran a simple micro benchmark. And in the micro benchmark, the computation we were doing in each task was something very simple, like we were computing the sum of a bunch of random numbers. And the main idea being here that let us stress the scheduling system to see how long it takes to do the scheduling. So the orange bars here represent what I like to think as the scheduling overhead or the coordination overhead imposed by the system, while the green bar is like the useful amount of work done. So you can see that when we have a smallish cluster, let's say 4 to 16 machines, the balance is quite reasonable. It's like 25 to 30% of the overall execution time. But when we go to 128 machines, we find that about 70% of the time is taken up just by these overheads, and there's only 30% of useful work being done. Or to put it another way, if we want, it's almost impossible to run anything which is less than like 150 milliseconds per like one of these jobs at a scale of like 128 machines. And as you can imagine, this gets worse as you scale your cluster to, let's say, 1,000 machines and so on. So now that we have a grip of the problem, how do we go about addressing this? So the main insight that we use in this work is that the DAG structure that we see across a number of these iterations, they actually remain the same. Thus, for example, let's say we have the first microbatch and then the second microbatch. The structure of the job that we're scheduling, it remains constant across a bunch of these microbatches, and thus we can reuse the scheduling decisions. Or these expensive algorithms or this communication we're doing, we don't need to repeatedly do that over and over again. So from this simple insight was born this idea of group scheduling. And the idea being here that instead of scheduling one of these iterations at a time, let's schedule a group of them at a time. So what that means is that, let's assuming we have one stage in each iteration, our original execution looks something like this today. And what we're proposing is we'll make it look something like what is shown in the bottom of the slide, where we have 2 iterations that are being scheduled at each time. Now, the trade-off here is that we're doing this fault tolerance and scheduling now at these group boundaries instead of at these microbatch boundaries. So we're sort of coarsening the granularity of scheduling. So how much does this help? So we redid the same benchmark that I showed you before, where we were computing the sum of random numbers, just a micro benchmark. And the blue bars here show how Apache Spark works today, where the latency goes to around 200 milliseconds at 128 machines. Now, in Drizzle, we can actually vary the group size. So the first thing is, like we set the group size to be 10, and that brings it down to around 21 milliseconds at 128 machines. But if we push it even further to, let's say, group size of 50 or 100, we can even come down to around 5 milliseconds of like overall execution at 128 machines. So as you can see, this has like tremendous impact from just like doing the simple idea that we'll group a bunch of these iterations together. So now, I've talked a lot about group scheduling, but what happens to these shuffle operations that are there, and especially these shuffle operations that were being coordinated by the scheduler in existing architectures? So in order to address that, we use this technique called pre-scheduling shuffles. And the idea here is really simple. So what we do here is that I'll first walk you through how the existing shuffle implementation in Spark works, and then show you how we can actually get the scheduler out of the way when we're doing these shuffles. So in existing Spark, what happens is that we first launch these map stage tasks that is shown in green out here, and then they produce some output, which is this intermediate data shown in these like blue boxes. Now, after this map stage finishes, we do some coordination, and then the driver launches these reduce tasks that are going to actually process the map outputs. Now, as a part of launching the reduce task, the scheduler also encodes where this data needs to be fetched from, and then the data transfer happens over the network. So at a high level, the main characteristics of this existing architecture is that the driver sends some metadata, and then the tasks pull data in order to complete the transfer. So in pre-scheduling, what we do is we try and remove this centralized synchronization in the middle by launching these reduce tasks ahead of time. So for example, if we had 2 reduce tasks like in the previous one, we first launch these reduce tasks on the cluster. And following that, we then launch the map tasks that are actually going to produce the data. Now, when these reduce tasks are first launched, they're in sort of a zombie state where they're just waiting for the input, and they're not actively running right now. And once their inputs are ready, we can then trigger their execution through these data transfers. So at a high level, what happens here is that we pre-schedule these downstream or reduced tasks on executors, and we trigger these tasks once their input dependencies are met. So how much does this help? So this is similarly a micro benchmark as I was running before, except we are also doing a shuffle in this micro benchmark now. And the baseline here is Apache Spark. And again, this takes around 250 milliseconds or so when run up to 128 machines. Now we Also experimented with just adding only pre-scheduling, like not doing group scheduling in this case. And that gives you some limited benefits. Like it gives you around like 20 milliseconds benefits or so at like 128 machines. But it's in combining these two techniques that we're actually able to get the most out of it. So when we combine these two techniques and we set the group size to, let's say, 100, we're able to process this two-stage job with a shuffle in it in less than like 50 milliseconds, even at like 100 machines. So this is some of the basic design that's gone into this Drizzle project. There are a number of other research ideas that we're working on, and I'm going to give you a short overview of a few of them today. I'll specifically talk about how we can go about selecting this group size and also some integrations that we can do with query optimization and for like machine learning algorithms. So one of the trade-offs that I mentioned when I talked about group scheduling is that we're sort of coarsening this granularity of coordination. So what are the effects of that? So if we set group size equals 1, then we get back the batch processing architecture that we have today. And if we set the group size to be infinity, then we get back the record at a time architecture that I talked about earlier in the talk. So by setting this group size in the middle, we're sort of getting a hybrid architecture, which is in between these two extremes. So there are trade-offs in these two extremes. So on one extreme, we have very high overhead for execution, but there's a small window for fault tolerance. And on the other hand, we have low overhead, but a large window for fault tolerance. So to balance this, selecting this appropriate group size becomes an important problem. And we're looking at some techniques where we can automate this so that the user doesn't need to go and select this group size. So one of our techniques here is to actually build a tuning algorithm that can adjust the group size based on what your application is doing and how large your cluster is. So for example, we have this tuning algorithm which can measure the scheduler delay and the execution time per group that's executed. And then based on whether the scheduling delay is too high or too low, it can adaptively make some changes. So for example, if we set a threshold, like let's say if I want my overheads to be within 10% of the overall execution, then if our overhead is greater than that threshold, we can increase the group size. If our overhead is lesser than the threshold, we can additively decrease the group size. This is born out of some inspiration from looking at TCP congestion control scheme for those of you who are familiar with networks. The other aspect that I'm really excited about is how Drizzle can be integrated with query optimization. Specifically, there are two kinds of optimizations that we can do in a system like Drizzle. The first is within one of these batches, so an intra-batch optimization, where we, let's say, use code gen or vectorization or some of these techniques that are well studied in like Catalyst, the existing Spark SQL engine. But we can also enable some new optimizations which occur across these batches, or these inter-batch optimization, which could actually change your query plan based on how your load is changing. So for example, let's say during the day you get a lot of queries from America, and during the night you get a lot of queries from like China. So then what might happen is that your query plan that you use could actually be different based on how your load is looking or how your data is looking. And this is some techniques we want to study as a part of our future research. The other thing that we're trying to work with in the future is how we can integrate Drizzle with machine learning algorithms. So this kind of iterative pattern that we see in streaming is also present in a number of like machine learning workloads, like gradient descent, PCA, and so on. And the idea here being that the model that all these machine learning algorithms are training can be stored in some shared state, like in some shared storage system. So to do this, we are exploring some integration with open source parameter servers as well. And we believe we can get some of the similar benefits of these parameter server style systems while using Spark for like scheduling, coordination, and so on. So quickly, I'm going to walk you through some of the evaluation. Jan in the keynote introduced this like Yahoo streaming benchmark that we ran to evaluate a number of characteristics of Drizzle. Specifically, we evaluated the latency that we can get while we're doing streaming, and also the throughput and the fault tolerance properties. In this set of experiments, I'm going to compare Spark 2.0 with Flink 1.1.1 and Drizzle. And these were run on Amazon EC2 R3.extra large instances. So to begin with, a quick description of the benchmark. So the Yahoo streaming benchmark was built to compare a number of stream processing engines, and there are a number of ad events it simulates on these machines that are coming across all of the machines in your cluster. And it computes a windowed aggregate per ad campaign. And the latency that we measure is from when the last event in the window happened to when it was like processed. So let's say the last event in my window happened at time t. At what time did I actually finish processing that last event? So the latency that we measure comes out as a CDF across a number of these ad campaign buckets. And to start with, let's take a look at how an existing system like, let's say, Flink works. So in this case, this is a CDF of latencies we see with Flink, and we see that it performs pretty well. Like it gets around 300 milliseconds or so on this 128 machine cluster. Now, if you take a look at Spark running out of the box, the median latency is much higher. It's around 1.2 seconds or so, and the tail is also pretty long as well. Now, with Drizzle, we're actually able to bring down the latency significantly and almost get around 350 milliseconds at median, being very close to what the Flink performance is. Now, this is running the query without doing some of the optimizations that I mentioned. And one of the things that we found out by looking at this is that we can actually push down some of this aggregation that's happening in the benchmark onto the map side and thus reduce the amount of network traffic. So that's this orange line here called as Drizzle optimized. And in this line, what we see is that the median latency can be further pushed down to around 100 milliseconds or so, showing this is kind of achieving the best of both worlds, where we're using the good parts of batch processing, where we're able to do this kind of query optimization, but also we're able to use some of the best parts of the record-at-time systems in terms of lack of coordination. So that's an idea of how the latency looks. In terms of throughput, we ran a weak scaling experiment where we fixed the amount of throughput per machine, and we measured the latency at each of these throughputs across a number of different machine sizes. And what we see was similar to the previous graph. So the previous graph was only showing this number at 20 million events per second, but even at lower time granularities, Spark's latency is around like 800, 900 milliseconds right now. Flink similarly gets much lower latency, around 200 milliseconds or so. And with Drizzle, at low latencies, low throughputs, we're actually doing a little bit better. And Drizzle optimizes, of course, much faster than any of these existing things. So that's in terms of performance. What about in terms of fault tolerance? So with the same benchmark, the thing that we did here is we killed one of the machines at the 4-minute mark, which is this 240-second line out here. And we tried to measure how long it takes for the system to recover to its original processing state. So the orange line here is Spark. We see that the initial latency is around 1 second, and it takes a little bit of a hit when the machine fails, but it quickly recovers. So it has good fault tolerance properties. Now, Flink, on the other hand, has a much lower operating latency, around 200 or 300 milliseconds, like we saw in the previous slide. But on machine failure, it's much more expensive. The main reason here is that Flink actually has to stop all of the tasks that are running on all the machines and then restart them from a checkpoint. And on 128 machines, this takes around 10 seconds or so. But it also takes time to catch up. So once you fall behind in a streaming system, you also have to catch up. So that takes around 20 or 30 seconds for it to catch up to what it missed out. We see that Drizzle, again, is able to achieve sort of the best of both worlds, where we have low operating latency, but also when the machine fails, the amount of time we spend in the latency that increases is also quite small. So a number of you are probably interested in wondering what is the future of this and what are some of our plans going forward. And I thought I'd give you a small update in terms of what we see as in terms of open source going forward. So the code itself that we use to develop this project is open source in the AmpLab GitHub page that's shown out there. And we have opened a number of Jiras on the Spark, on the Apache Spark Jira in order to discuss integration of Drizzle with Spark. So there's a big one which is at the bottom, which is shown there, which is to have general design discussion. And a number of smaller scheduling improvements that we made have been addressed as separate Jiras as well. So I'd like to conclude this talk by summarizing the fact that it's very important for these large-scale streaming systems to have low latency during execution and also while adapting to changes. And we found that by decoupling the execution granularity from scheduling granularity, we were actually able to achieve this in this Drizzle project. Our main insight is that we can amortize these overheads using these techniques called group scheduling and pre-scheduling. And as I mentioned before, the source code is on GitHub right now. With that, I'll take any questions you have. Thank you.
So who we got with questions here?
Alex Crowitz. I noticed in the fault tolerance study that relative to Spark, Drizzle had a pretty good recovery. I sort of expected that it wouldn't have as good a recovery time just because for each host there are more processes that are going to be affected.
Yeah, that's a good question. The question is about how does Drizzle's fault recovery compare to like Spark's fault recovery? I think it's a little bit hard to read in this graph because the graph is stretched out to 20 seconds to accommodate the Flink line out here. But there is a little bit of extra overhead in Drizzle's fault recovery, and I didn't quite cover it in the slides because I didn't get time to do it. Let me see if I can pull up one of the backup slides that I have for it. So this shows at a very high level Drizzle's fault recovery. So what happens is that since we do this pre-scheduling, where we schedule some tasks ahead of time, when the machine dies, we actually need to account for some promises that we made that are no longer true. So we do need to schedule a few extra tasks when there's a machine failure that happens. And also we roll back to the beginning of one of these groups. So if you run a group of like size 10, we have to roll back the execution to the beginning of the group. So there is some additional overhead that does happen in Drizzle fault recovery. But the thing is, the benchmark was evaluating these windows at a 10-second granularity. So a lot of the overheads actually are accounted for within such a coarse granularity. So this is another one of those things where we have more fine-grained numbers that show exactly how much this overhead changes. We do pay some additional overhead for doing this more coarse-grained coordination. That's a good point, yeah.
Other questions?
So in one of your earlier slides, you had some breakdown of the overheads as you increase the number of machines in the cluster. Mm-hmm. I wanted to see if you could expand on the reasons for the different overheads.
Sure. I think you are talking about this one. Yeah. So in this case, what's happening is we're running this like two-stage job, which is doing a shuffle as well. And there are 3 bars here. So one is the scheduler delay, and this includes this time for doing all the scheduling algorithms that I talked about, and also for sending these RPCs to these machines. So there's some linear overhead that we get when we have to talk to like 128 machines as opposed to talking to like 4 machines. And a lot of the algorithms inside the scheduler are also linear in terms of the number of tasks that are run. So at 128 machines, we run 512 tasks here. In 4 machines, we run only 16 tasks. So some of that overhead is much smaller. The task fetch bar there, we use a broadcast variable in Spark to send a bunch of metadata when we are scheduling things. So the task fetch is the amount of time it takes to fetch the broadcast data on the executors themselves. Now, this also scales. It doesn't scale linearly. It scales sublinearly because we use this torrent-based broadcast in Spark. But that's what that lighter orange bar is out there. Now, if you look closely, even the green bar is growing as we grow across the number of machines. And this is because our shuffle implementation, we are sending like messages from each mapper to each reducer. So if you have 128 or 512 mappers as opposed to 16 mappers, you actually need to send more shuffle messages. This is not imposed by the scheduler. This is just a characteristic of the job itself. But there's some amount of overhead in sending these shuffle messages, deserializing a shuffle block, and like executing it. That increases this green bar as well as we go from 4 to 128. Yeah. Did that answer your question? Thanks.
Did that answer your question? Yes. Yes. So let's see here. We are actually officially out of time, but we can go ahead and take your question here if it's really quick.
What's the plan for merging into main Spark?
Yeah, so that's a good question. So as I mentioned before, so we have a few JIRAs that are already open to discuss merging this with Spark. So the way I see it is that there are a lot of like code that we wrote here because there are a bunch of techniques that we're combining to get this effect. And I think we're going to merge them one at a time, like as a phased out kind of like process. So specifically, for example, this pre-scheduling thing, it can help any of the Spark applications that you run. It's not actually restricted to like streaming per se. So we might be able to push that in a little bit more easily. And these pieces actually do compose reasonably well. Like we can check in one at a time. So we have sort of a phased rollout in mind, but this is also up for discussion on the community JIRA. So I think I put up some of the JIRA numbers out there. So if you follow that, I think you'll get a better idea of what time frame we're looking at. Yeah.
So thank you very much.
All right,
Excellent
thank you.
talk.
Yeah.